So now we want to really take a look at where the electrons are going to be located inside the atoms. So for this section, we're going to look at quantum mechanics because this provides an intellectual structure for describing our properties of the atoms and molecules. And for this section then, every atom is assigned 4 different quantum numbers. These are the N number, the L number, the M to the L, and the M to the S numbers. And so you'll be exposed to all 4 of these numbers, and this is kind of like an address for where the electrons are going to live around the atom's nucleus. So these numbers uniquely define the spatial distribution and the spin state of the electron, just like our addresses define where we live inside our cities. So we can envision every electron in terms of its characteristic energy, the size, the shape, the orientation, and the spin of the electron. So our first quantum number, the N number, we've already been exposed to. These are the orbital shells, and so they correspond to the periods in the periodic table. And so this is kind of what we were talking about as far as the layering that kind of reminds me of the onion shape. And this is a little bit oversimplistic because the shapes of the orbitals we're going to see are very dramatically different. But you can kind of think of the atom as having layers, just like the onions do. The farther then a shell is from the nucleus, the larger it is, and the more electrons it can hold. So the higher the energies of those electrons. So the electrons towards the outside of the atom, the farther away they are, the more energy they have. The smallest shell is going to be closest to the nucleus, and this one is labeled as 1. And then as the increasing shells come out, that would be 2, and that would be 3. And these guys correspond to these rows on the periodic table. So this is our first quantum number. This is the N number, and it corresponds to increasing the layers of the onion that you're going to have where the electrons can be found around the nucleus or the core of the atom. So this is a nice indication just to show you where the lanthanide and the actinide elements are going to fit into the periodic table, because this becomes important now as we're thinking about how the electrons are arranged in these outer shells. So we kind of always put them outside of the periodic table directly, and this is just because the size of the periodic table becomes so big it doesn't fit on one piece of paper very well if you put the lanthanide and the actinide rows where they belong in these 7 shells. So there's only 7 shells. If you get larger than this, it's kind of like when we would have a satellite, if we put it into orbit in space around the Earth. Once you reach so far, if you get too far away from the Earth, the gravitational pull of the Earth is not good enough anymore to hold that satellite in there. The satellite would escape from the Earth's orbit, and it would just keep going in directional way. And we've sent, satellites out into space in this kind of fashion. The same thing is kind of true for the atoms as well. You can only go out so far before the electrons no longer are going to orbit that nucleus. They would become unstable and they would escape from the attraction to the positively charged protons at the nucleus of the atom. And so 7 seems to be that magic number. If you get bigger than 7 shells away from that nucleus, it's too far for those electrons to be held into that atom anymore. And so we don't see any atoms that have more than 7 shells where electrons can be housed. The lanthanide and the actinide series actually fit inside rows 6 and rows 7 of the periodic table. And if we place them in their correct place, you can see these internal transition metals would fit into the periodic table just like this. They would kind of split the periodic table. So you still have the first 2 rows, the alkali metals and the alkaline earth metals, and then you would have the lanthanide and the actinide series come in here, the inner transition metals, and then you have the regular transition metals that are shown up here in the periodic table. And then you would have the rest of the group 1 or A family elements that would be listed right here. So this is the way the periodic table actually is, but you always seen it shown with the lanthanide and the actinide series pulled out from it. But it's important to note that for our N numbers, the lanthanide series is in row 6 and the actinide series is in row 7, and they should be placed right here in the periodic table. So that's our first quantum number, is the N number, so these shells. Within the shells, there's subshells. So these would be like apartment complexes. So if you've seen an apartment complex, the whole apartment complex would be akin to the shell or the first quantum number, the N number. And then the subshells would be like apartment buildings within the apartment complex. You can still house a whole number of electrons in the subshells, but you might be in building 1 versus building 2, building 3 of the entire apartment complex. So the orbital subshells are going to represent the L number for the quantum numbers. So this is the second number of the address. So within the shells, the electrons are going to be further grouped into these subshells, and there's 4 possible subshells that can exist within each layering. And we'll see that the first one is called the S subshell, the P subshell, the D subshell, and the F subshell. So again, these are like apartment buildings where electrons can be housed inside there. The S subshell is the smallest type of apartment building that you can have. And in the first period, or the first row, it's so close to the nucleus of the atom that it can only fit the S subshell. It's not big enough to have any of these other subshells inside there. So when you move out and you have the second layer, so this is again the shell number, this corresponds to the periods on the periodic table. If you move down to the second row, it's big enough to house both the S subshell and a P subshell. The third shell, as you get even bigger, can now house the S, the P, and the D subshell. And then when you get to the fourth level, it can house S, P, D, and F subshells. And after the fourth subshell, the fifth, sixth, and seventh also house these 4 subshells within them. So these are like, again, the apartment complexes, and then these are the apartment buildings within the complex, and then you have the orbitals, which are the individual apartments that can exist within the apartment building. So for the first shell, you only have the S apartments that are going to be available, and within the S apartments, there's only a single apartment in there. So this is like a small cottage. So you only have 1 apartment or 1 orbital where the electrons can be housed. Within the second shell, there's the S apartment, which is again the small cottage. You only have 1 apartment in the S building. The P building, however, has 3 different apartments in there. It has 3 orbitals where electrons can be housed. And then when you get to the D subshell, the D subshell actually has 5 apartments within its building where electrons can be housed. So each S subshell has 1 orbital, each P subshell has a total of 3 orbitals, each D subshell has a total of 5 orbitals. When you get down to the F subshell can hold 7 orbitals. So again, these are like an apartment complex. These are the individual apartment buildings, and these are how many apartments are held within that single building. So for the S subshell, there's 1 orbital. P, there's 3 orbitals. The D building has 5 orbitals, and the F building has 7 orbitals. So each different orbital has a different shape. So the orbitals in the S subshell are spherical in nature, but the orbitals in the P subshell are roughly dumbbell in shape. So we said that the P subshell has 3 different orbitals in it, and each of these orbitals is dumbbell shaped, so the electrons are kind of spinning around in this dumbbell pattern, depending on which P orbital they're going to be housed in. So you can have one along the x-axis, you can have one along the z-axis, and you can have one along the y-axis. So we've got 3-dimensional space, and we have 3 dumbbell-shaped orbitals within the P level. The D level looks a little bit more complex. There's going to be 5 different orbitals, and the F subshell looks even more complex with 7 orbital patterns. So within each orbital, you can house a total of 2 electrons. That will be the maximum number, and that's going to be the last quantum number that we get to, the m to the s. And we will talk more about that in a minute. So within an s orbital, though, you can house a total of 2 electrons. Within the p subshell, the p subshell has 3 different orbitals. Each one can contain 2 electrons in there. So you can house a total of 6 electrons inside the p orbitals. Okay, so when we're thinking about these quantum numbers then, we're going to have a few principles about filling these different places, or the address or the apartment buildings where the electrons are actually going to go. So our ground state electron configuration. So Z number of electrons. So this is the atomic number of the atom. Remember, our Z number is going to be the number of protons within the given atom. In this case, the Z number of an elemental form of an atom is going to have the same number of electrons as it does the protons. So this is the Z number of the electrons. It's talking about the atomic number. So that's listed on the periodic table. We can find that very easily for any different element. So that's the ground state electron configuration. These are going to be placed into the different orbitals, which represent our apartments now, according to our following guidelines or our following rules. So there's 3 main rules that we have to follow. The Aufbau principle says that electrons have to go into the lowest energy orbitals first. So the lowest energy orbitals are the ones that are going to be closest to the nucleus of the atom. They have to go into the lowest shells first, and within those shells they have to go into the closest subshells. And then the Pauli principle is telling us that no more than 2 electrons can fit into any one orbital. So that's what we just kind of got done saying. And when they go into these orbitals, their spins have to be opposite and paired with one another. And then finally, you've got Hund's rule. So this states when there are orbitals of equal energy within the subshell, the electrons first go into different orbitals with parallel spins one at a time. And so what this basically means is that if you have a subshell, like the p subshell, that has multiple orbitals, so our p subshell has 3 different orbitals, the electrons, they want to live alone if they can. So if there's only 3 electrons that can go into that subshell, the electrons will go as singles into each of those different orbitals. So if we go back and we're looking at our p orbitals, if we only have 3 electrons that are going to go into these, 6 can go in, but if we only have 3, depending on what element we have, those 3 will choose to go and live alone. They'll each choose to go into their own apartment by themselves and be individuals. They won't want to be paired with each other unless they have to. So if we had 4 electrons going into the p orbitals, we'd see the filling go. 1 would go here, 1 would go here, 1 would go here, and then that 4th one would have to pair up with one of the other electrons in the p orbitals. And so that's essentially what Hund's rule is stating, is that the electrons, they want to live alone if they can. And that makes sense, right? Because electrons are both negatively charged. They don't want to be close to each other. So they repel each other. And they only become kind of close to each other within the orbitals if they have to. And that's also the reason why only 2 electrons can fit into an orbital. Otherwise, the repelling force becomes too great and the other electrons would be kicked out. So the 4th quantum number deals with the electron spin. And so this deals also with Pauli's principle that no more than 2 electrons can be paired within any one orbital, and their pairing is going to deal with their spins. So one has to have the spin up and the other has to have the spin down. And so what that means is actually these guys are rotating on their axis. So it doesn't really mean that they're like moving in a directional pattern, but they're like the Earth. The Earth spins and rotates on its axis every day, and that is going to make up our day length in the case of the Earth. For the electron, it also will spin on its axis as well. And so one of the electrons has to spin clockwise, and the other electron has to spin counterclockwise. And so one is called spin up, and the other is called spin down when you're representing this phenomena. But it's actually the electrons spinning on their axis. So this is a very nice slide that is going to demonstrate and consolidate then the quantum numbers that we've just talked about. So the first quantum number, the n number, is going to be the shell number. And again, this corresponds to the periods or the rows on the periodic table. There's a total of 7 shell numbers, and that's it. You can't go in any greater layers of your onion after that. So again, this is akin to saying you have an apartment complex. These subshells that you have within the apartment complex are going to be essentially the apartment buildings. So you have the S type of apartment building, you've got the P type of apartment building, you've got the D type of apartment building, and you have the F type of apartment building. And they keep getting bigger in size because each of these different apartment buildings can house a different number of apartments. And that's going to be our number of orbitals that is going to be present within each of these subshells. So the S subshell, again, is the smallest. It contains 1 orbital. Each orbital can then have a maximum of 2 electrons that are housed within that orbital. The second subshell is bigger because it's going to be outside of that first subshell, and so that's the second layer of the onion. It can house 2 apartment buildings or 2 subshells, the S and the P subshell. The S subshell again only has 1 orbital. The P subshell has 3 orbitals, and so each orbital can contain 2 electrons. So this one can house 2 electrons. This one can house a total of 6 electrons because there's 3 apartment buildings. So the second shell can house a total of 8 electrons maximum. Now you've got S in the third level, you've got S, P, and D apartment buildings or subshells, and each of these get bigger and bigger. So the S subshell only has 1 apartment, and so this is our 1 orbital. The P still has 3. The D apartment building's got 5 different orbitals. So you can have a maximum of 2 electrons in the S orbital at the third level. You can have 6 in the P, and you can have 10 in the D orbitals because you've got 5 orbitals here. So in the third shell, you can house a total of 18 electrons. So for atoms that have 3 layers on them, they could house a total of 18, 26, 27, 28. They could house a total of 28 electrons in their shells. When you go up to the 4th level, you're going to add on that F apartment building, which has 7 orbitals, and so you can house 14 more electrons in the 4th level. The 5th, 6th, and 7th each contain these 4 subshells and can have a maximum then of the 32 electrons in those outer shells as well. You don't keep getting more orbitals because the space around there to make these orbital shapes is just not great enough to house any more orbitals around the atom. So electron configurations then are going to be described by writing the shell number. So I think this is a good place to stop for this section, and then we'll continue on with how you actually fill the electron shells in the next talk.